Hey everyone, we're back to talk about lecture 22 about the order and accuracy, the order of accuracy and numerical stability for numerical integration methods. So last time we developed for Euler's method, Hume's method, and the Runge-Kutta method for numerically solving differential equations. We didn't really talk about how accurate they were. We could see if we change some of the parameters that we put into those algorithms, like the number of points that we sampled or the step size of the sampling in time, we could see that the accuracy changed visually. We didn't really quantify how it changed. So that's what we're going to look at today, which is a really important feature of these algorithms. We're going to go back to looking at this second order scalar differential equation, x double dot plus 4x is equal to 3 sine 2t. So non-autonomous. Initial value problem, and has an exact solution, this guy here. Sines and cosines with a t cosine t term that comes from forcing at the fundamental frequency, because this is a harmonic oscillator. So if we want to apply our numerical methods, we want to convert this to a system of first order differential equations, and so that would look like this. And we can find that the exact solution looks like this, which is really just this. And since the other state variable is x dot, the derivative, right? Okay, great. So we're going to apply forward Euler's, Hume's, and Runge-Kutta. So in your notes, I've written out the functions as I've done them in MATLAB for these for this video. I'm going to just share my MATLAB with you because it'll be easier to look at. I'll just talk through how I coded it. Okay, so here's MATLAB. Okay, hopefully you all can see that. So first of all, I guess let me make my font a little bit bigger. Might be easier for you all to see. Okay, that's probably better. So I'm going to talk about the functions, how I coded them. So I coded the function for the right-hand side of the differential equation itself, written as a system of first order, so this is vectorial, fine. And how do I code for forward Eulers? I'm going to use this function here. I'm going to input a number of steps and a step size h in an initial condition, which is going to be a 2 by 1 vector. I'm going to initialize time as 0 and y as some initial condition, why not? And then I'm going to go forward for n time steps. So the update for time is just going to be adding the fixed steps of h at every time step. And for y, it'll just be the forward Euler's algorithm. So y at time k plus 1 is y at time k plus h times the functional value for tk and then y at time k. So that's forward Euler's. Pretty straightforward. For Hume's, it looks exactly the same except this equation for y changes, right? Now I have 1/2, so that's the divided by 2, h times the formula that we had for Hume. So f at tk yk plus f at tk plus 1 yk plus h ftk yk. So the input to this f in the numerator came from forward Euler's. Finally, the last algorithm is Runge-Kutta, which you can see coded here. Same initialization, then for every time step, time moves forward in the same way as before. And I define these 4 different auxiliary functions, so f1, f2, f3, f4, in terms of some function f. So that's the function that I defined upstairs, the right-hand side of my differential equation. And then I combine them according to Simpson's rule to get the discrete time update for Runge-Kutta. So those are the 3 different numerical solvers that I coded. I have an initial condition, step size, a number of steps here, the multiplication of which gives us the amount of time, say, I'm actually numerically integrating for. And then this is evaluating one of those forward Eulers in this case and plotting it. And I have an exact solution here for this plot, but I just wanted to walk you through how I coded and why, and I'll put this up on the Canvas website as well. So let's go back to the handwritten notes. So this is how I'm applying these different algorithms. And the next page of the notes has kind of a more specific MATLAB code here for how to actually run this function. So here's one for example, and generate this plot. So you can see that in the MATLAB code with a bit more resolution. But here's the plot that I get from the code that I just showed you. So this is forward Eulers. So the initial condition that I put in was 2, -1. So it's starting here and it spirals and then starts to go out. And the exact solution is a solid line. The numerical integration is the dots. And you can see as time goes forward, it gets worse, which kind of jives with what we saw last time, looking at the accuracy of just the first element of the 2D state. So this is using in a step size of 0.05 and 200 time steps. So we go up to a time equal to 10. If I instead do Hume's method with the same parameters, h is 0.05, n is 200, I get actually a really nice match. So much better than Eulers, as I would expect. So how can I quantify this idea of error? Here is the concept. So I start at some time, say 0, and I want to estimate the state at some time, call it Tmax, using a numerical method. So that's the Tmax is actually the product of the number of time steps times the size of the time steps. The final error should look like, with the true functional value is minus the nth step, the norm of this. And I'm going to say that this looks like, fit this with a function that looks like a constant c times h, the step size, to the p. So as h gets smaller, this guy's going to get more accurate, right? I'm going to call the integer p the order of the numerical method, because it tells me how quickly this term goes to 0 as h goes to 0. If p is equal to 1, I call it a first order method. If p is 2, it's a second order method, and so on, meaning that this goes to 0 like x or x squared. So if I have a first order numerical method and I multiply the step size by a half, so I had c h over 2 to the p, and p is equal to 1, then if this is called my, say, my error, we'll give it like a notation. Call it this 1/2 factor error. This guy is actually 1/2 times ch, which is my original kind of error, ch to the p, right? So multiplying the step size by a half multiplies the error by a half. For a second order system, if I look at what the the error, maybe we'll make this a 1 here. Error for a first order, error for a second order system. If I multiply the h by a half, but now my exponent is 2, I end up multiplying my original error by a 4th. Similarly, a fourth order numerical method, when I multiply the h by a half and then raise it to the 4th power, I get 1/16 of my original error. And so if I have this model for the error, this idea that the error is ch, oops, this h should still be squared here. I have this model for the error here, then I can look for these factors. When I compare my numerical and my exact solutions, if I have a system that has an exact solution that I know, I can then use that to understand the order of my numerical method. So looking at this, it tells me a way to define something about my numerical methods. So I'm going to show you a MATLAB code that does this convergence study to calculate this error between y at time 10 and the nth step of y when h is 0.05 or 0.0025 or 0.005 or 0.0025, so a half of that. And we look for the ratio of these errors. So what I'm going to say is if I divide h by 2, what happens to the error? When I look at the ratio of these errors, do they get divided by 2, or will those show up as a factor of 1/2, 1/4, 1/16, or so on? So here's the code for that. I will also upload the MATLAB code for this. Will be lecture 22 error. So I'm going to compute for forward Euler. I'm going to take the difference between the exact solution and the final term from either forward Euler with 0.005h or 0.0025. And then I'm going to take the ratio of those. So if I run this, you don't have to go through it with MATLAB, but I'll just tell you, running this gives me an output for the ratio of these errors of 2.0066. And it tells me that the error between these two, which if I just, since I know I divided h by 2, if I calculate this out, that's really just 2 to the p. This is an approximation for error 1 over error 2, the two different errors I defined using the h's. And this looks like 2, then p should be like 1. So forward Euler's is a first order numerical method. So what I can do is I can use a system for which I know the exact solution to compute these errors exactly to understand the order of my numerical method. In real life, we're going to use Euler for systems that we don't know their exact solution. But before we do that, we want to get a handle on how accurate this is and how the accuracy of the results scale with the step size. Hopefully that makes sense. So I'm using this kind of reference problem that I know the exact solution for to study how this error changes. So I can do a similar thing with Hunes. If I run the same algorithm, but I change forward Euler's to Hunes, I get something that looks like a ratio of 4, around 4. So I have some 2 to the p is like 4.0069. which implies that Hunes is second order. If I do Runge-Kutta, I get something like 16. So 2 to the p is like 16.1486, which means that Runge-Kutta is fourth order. This goes well with what we saw last time, that we saw for the same step size. Hunes did better than forward Euler's, but Runge-Kutta did much, much better. Okay, I hope that makes sense. Let's look at another example problem. So this was about the order of these algorithms. Now let's talk about their accuracy. Let's start to talk a little more about the idea of error. So let's consider this initial value problem. Second order scalar IVP has a known exact solution, this guy here. I'm going to convert it to a system of first order equations. And I have this exact solution, right? X dot. Okay. So if I want to apply forward Eulers for some step size and some number of steps, again going from 0 to 10 in time, I get this plot. H is 0.05, N is 200. And I can see, you know, the solid line is the exact, the dots are forward Eulers. It does a decent job of approximating, but where the dynamics happen kind of quickly at this sharp bend, I get a little bit lost, right? I have a point down here. So it makes me a little bit worried. What if I make my step size a little bit bigger? What if I make my step size 0.08? So if I do that, and I'm changing n so that I keep always going up till time is equal to 10, when I do that, I'm getting a bit of a disaster, right? I match for the initial condition at 10, 0. And then after that, I'm never really close to the line. I'm bouncing above and below over and over. So that looks problematic. Even more problematic if I make my step size 0.1. So that forces my n to be 100 to keep going up to a max time of 10. Stuff goes pretty poorly, right? Look at these axes. 10 to the 18, 10 to the 17 means the solution is blowing up in like 2 directions at once. It's a big disaster. We can't see the exact solution, obviously, because it's 18 orders of magnitude smaller than this plot, and bad things have happened, right? So why? Why did bad things happen? Because if I look back, so now I'm on page 8 of the notes, if I look back at my original system, this was y prime is equal to ay, right? Linear system should be very, very straightforward because I have this matrix, 2 distinct eigenvalues, and they're both negative. So in continuous time, I should have that the equilibrium at the origin is asymptotically stable. So what's the problem? So when I do this approximation, this numerical approximation, even though I'm trying to approximate a continuous time system, it is really discrete. That's why we spend so much time talking about discrete time and continuous time systems. When you do stuff computationally, you are always forced into a discrete regime. And so you have to be sensitive to the differences between those two different ways of looking at time. So Euler's method generates approximations according to these difference equations, right? Y at k plus 1 is y of k plus h times the right-hand side of the equation, right? F at tk and 1k. So what is that for the equation above? That's really ayk. So I just have this discrete time equation, right? So that looks like some a tilde yk. This guy again has a fixed point at 0, 0. Call it y star. But for what h's is it asymptotically stable? How do I know that? Well, if I have a discrete time system, remember, whenever I want to move forward in time, it's like multiplying on the left by another a, right? So I had something where I was always looking for, I had a tilde yk, I was really looking for a tilde to the k times y naught. So the condition for the eigenvalues for stability wasn't this condition up here where it has to be negative because solutions in continuous time look like exponentials. So I want e to the negative t, right? So it'll decay as time goes forward. No, instead for discrete time, I want eigenvalues for a tilde that live in the unit circle. So the question really is, for what h's is this point asymptotically stable? Meaning for what h's are the eigenvalues of this matrix in the unit circle, right? So when they're less than 1, they're going to shrink, right? This will converge. If they're bigger than 1, a tilde to the k blows up and you don't get stability anymore. So what are the eigenvalues of this a tilde? So let's remember, if I have the eigenvalues of a matrix A, being lambda 1 and lambda 2, then the eigenvalues of I, the identity matrix, plus HA are 1 plus H lambda 1 and 1 plus H lambda 2. We showed that, we've used that, right? We know the eigenvalue equation can multiply by a scalar, still holds, the eigenvalues get bigger, and then if I add, just shifts the spectrum, right? If I add multiples of the identity matrix. So what does that mean here? If I have lambda 1 is -1 and lambda 2 is -25, that means, let's call it lambda 1 tilde is 1 plus h times -1, and lambda 2 tilde is 1 plus h times -25, so 1 minus h, 1 minus 25. So the h's I want to plug in are 0.05, 0.08, and 0.1. They're all less than 1. They're all between 0 and 1. So that's not going to be a problem. That's always going to be between 0 and 1. But let's compute the other ones. If I have h is 0.05, h is 0.08, and h is 0.1. I'm just going to do it really quick in MATLAB, and I'll write it down instead of showing you if that's okay. Let's see, what are those numbers? Okay. So 1 minus h, if h is 0.05, this is 0.95, 0.92, 0.9. So that's no problem, right? Always in the unit circle. However, this is minus 0.25, minus 1, minus 1.5. So I can see the problem, right? Actually, if I look back at my plots from earlier, when it was minus 0.25, I got a plot like this, which was stable, fine, no problem. When I had an eigenvalue of -1, I was this. I was not stable, but I wasn't going to infinity. But I certainly wasn't converging. And when I had h was 0.1, I went to infinity, right? Because an eigenvalue of 1 is not going to blow up, but it's not going to shrink, right? That makes sense, hopefully, to you with the plots that we've seen so far. And so what that tells us is that forward Eulers is not going to converge for every value of h. So we have to be careful with h's we choose. What about the other methods that we've looked at? Is the same thing true? So same problem, just writing it here so you remember. Humes uses this algorithm. If I write it, thinking of this as a yk, I can write it like this, which I can write in this way, which again is like an a tilde yk. So all I care about are the eigenvalues of a tilde in the unit circle. To understand if 0, 0 is asymptotically stable for the difference equations. Okay, and so what can I say? This is again just a way of shifting and scaling the eigenvalues of A to get the eigenvalues of this guy, right? So I had 1 plus h lambda 1 plus h squared lambda 1 squared over 2, 1 plus h lambda 2 plus h squared lambda 2 squared over 2. Oops, you can't see that. So I'm going to use MATLAB again just to compute this. So with h being, what do we have? 0.05, 0.08, and 0.1. What are those numbers? Okay, so again, this first one, if I have lambda 1 is -1 and lambda 2 is minus 25. Okay, you see that? There we go. So in that case, When h is 0.05, I have 0.9512. When it's 0.8, 0.9232, and 0.9050. No problem. And h is 0.05 for the second eigenvalue, 0.5313, 1, 1.625. Same situation as Euler's, right? Some values of h make the whole thing fall apart. And in fact, if I look when h is 0.08, I'm on page 10 of the notes now, you can see this plot, where again, doesn't go to infinity. So a to the k is not blowing up because it has an eigenvalue at 1, but it's not converging. So start this initial condition together, and then I'm never going to converge. And similarly, if I plot Runge-Kutta, not with an h of 0.08, because Runge-Kutta seems to converge for some pretty large step sizes, but an h of 0.125, you can see 10 to the 36, 10 to the 34. Bad things happened. So again, none of these algorithms work for all h's. For this a fixed h, some may work better than others, but for some fixed h's, maybe nothing will work. So all of these algorithms have what we call numerical stability issues. They may not converge. Points that are stable when I use continuous time may not be stable in discrete time. So in the next lecture, we're going to start to talk about a different class of numerical methods, numerical integrators, called implicit methods. And they have this really nice property that they are unconditionally stable, meaning they are stable for any value of h. And so it's important to learn about the methods that we did so far, because they can be really useful and really easy to implement for some values of h, but we have to then pay attention to convergence. Next time, we're going to look at methods where we don't have to really even pay attention to which h, but maybe just more difficult or different to think about in implementation. Okay, that's it. Bye-bye.